with the HDL code generation. So ideally, we can imagine that you have, or we have some MATLAB, a high level of abstraction MATLAB code or algorithm. We can just press a button and it will go directly to FPGA or SoC development board. But we know that in reality, I think you are, of course, really aware of that we have a lot of questions that should be answered or some specification that should be met before going to hardware. So going from a very level, an algorithm to hardware implementation isn't straightforward. We need to answer questions about hardware architecture, how we are implementing our algorithm. We need to see the effect of fixed point quantization on our model. So going from floating point to fixed point, how will be affecting and what error is introduced to our model. We need also to see if we have some legacy code, some handwritten code that we need also to integrate in our Simulink model. And finally, we need to see how we can implement directly into FPGA. So that's what we'll be visiting today. I know that you are already familiar with HDL coder, so, but if there's any aspect that you didn't, you will not see in my presentation, do not hesitate to mention it in the chat, and I can answer it later, of course. So the idea, like I said, is going from a MATLAB algorithm to hardware. And to do so, I like to talk a little bit more about MATLAB, why MATLAB, Simulink, and how we can separate these two environments. So usually we use MATLAB for large data sets to explore the mathematics, to visualize some data. Of course, we can do that in Simulink, but we like to keep MATLAB for like golden reference and reference algorithm in order to use them later on to compare them to what we have in Simulink. So in Simulink, Simulink is very well suited to explore timing, evaluate some architectures, and of course do some data type analysis. And that's where we can go from a floating point representation of our algorithm and later on our model in order to go a more fixed point representation of our model, right? So in other words, we can see MATLAB as where we can create our golden reference algorithm and even our implementation algorithm. And Simulink, it's where we can explore our architectures, our fixed point implementation, and later on generate code and explore even the optimizations that are provided with HDL coder. So if we go just back one step and visit the conventional HDL workflow, right? Going from behavioral model, functional model, developing HDL, all the way through integrating HDL and verifying it on the hardware. What we offer is not to break this workflow, but rather to replace some of the steps. So what we will be offering is more another way to create a functional model, developing HDL code and assessing the results or the quality of the code that we are having. And in that case, we'll stop talking about developing HDL code, but rather generating HDL code, right? So, and to generate HDL code or to modify our code, we'll not go and modify our code by hand, but rather we'll stick into Simulink, into the Simulink environment where we can modify the block settings, for example, modify some subsystem settings, some model settings, and finally modify the architecture if needed. Once we go into, for example, a specific application like wireless and digital signal processing, we can see that how, for example, we can modify the code directly from the architecture or the implementation architecture that you are using in Simulink, right? So the big idea behind HDL coder or code generation is to combine different representation of the same algorithm, like by using MATLAB, Simulink, Stateflow. You have a unified representation, add a layer of optimization that is provided with the coder tool in order to generate code. So of course we can generate C code, C++, PLC, and CUDA, but today we are focusing on HDL code, right? So that's the idea behind HDL code. I like to spend just 2 seconds, not maybe 2 minutes, on data types in Simulink and in MATLAB, because it's a stepping point, because later on we'll see how we can also have some trade-offs between the architecture that we choose, but also the data types that we'll be choosing. So usually in Simulink, you will be modeling by default by using a floating point data type, right? It's in double, but we all know that's something that's very efficient for hardware. So we'll need to go through to converge for a more realistic and efficient representation that is the fixed point conversion or the fixed point data type. And to do that, of course, you can do it by hand, but we also provide you with a tool that's called the fixed point designer that will allow you to iterate on your data types in your model in order to simulate. It will start with simulating and collecting the data ranges that you have. Later on, it will propose to you some data types, some fixed point data types. Once you accepted the propose, or you can adjust, of course, some of the data types, it will re-simulate and analyze the effect of that these conversions have on has on your model. In that case, you will go from a floating point representation of your model to a fixed point representation of your model through an iterative workflow. Of course, here you have the visual that you will be having, where you can the tool will assess the effect of every data type on its on your model. And if you're happy, if it meets your requirements, you can just accept the data types and move to the next level that would be generating the code. That's a small, I always like to talk about data types. It's something that's very important to hardware engineers, and MATLAB and Simulink being some high-level tools, high-level abstraction tools. You need to know that we always start from a floating point representation, and we need this step in order to converge to a more realistic and efficient representation of your model.